Hello, this is Ms. Moore, and today during chemistry we're going to discuss the equilibrium constant, or KEQ. Today's essential question: what is the equilibrium constant and how is it calculated? Let's start with a quick review or overview of equilibrium. So, most reactions do not go to completion. And when a reaction goes to completion, what we're saying is that all of the reactant turns into product. Okay. What normally happens with a chemical reaction is that it reaches a state of equilibrium when the reactions are then reversible. So during equilibrium, what's actually happening is that the products reform reactants at the same rate as the reactants are forming products. And the way you know that a reaction is reversible is the arrows, if it's written in equation form, because you're going to have arrows going from product to reactant and from reactant to product. A reaction that goes to completion would be one that would have a single arrow. All right, let's talk about the equilibrium constant. The progress of a reaction can be estimated by measuring the concentrations of reactants and products in moles per liter, which is also known as molarity. The equilibrium constant, which is K subscript EQ, is the ratio of product concentration to reactant concentration at equilibrium. So at the point when the forward reaction going from reactant to product is going at the same rate as the reverse reaction going from product to reactant. Okay? Pure substances, meaning substances in the liquid or solid states, are not included in the equilibrium expression or formula. Okay. All right, let's learn how to calculate the equilibrium constant. The formula for the equilibrium constant is KEQ equals square bracket to the x product times square bracket product to the x divided by square bracket reactant to the x times square bracket reactant to the x. Okay, so first of all, you do need to know this. Okay, make sure you know this. Okay, the brackets mean concentration of. So if we were to really read this, it would be KEQ equals the concentration of product to the x times concentration product to the x divided by concentration reactant to the x times concentration reactant to the x. Okay, and then let's discuss the little x up there. So I'm going to highlight these x's. You might want to do this. So these little to the x things, these subscripts. The subscript x is the coefficient from the balanced equation. Okay, and a coefficient, if you remember, is that big number we use in front when we're balancing the equation. Okay, before we move on to point 4, I want to point out that not all reactions have two products and not all reactions have two reactants. So on the top, you put all of the products, the concentration of each product to the power of its coefficient, and multiply them. If there's only one product, you don't multiply anything. If there's 10 products, you're going to multiply all 10. The same with the reactants. Okay, so point 4 now. If KEQ is less than 1, the reverse reaction is favored. And if you look, less than 1, reverse reaction. If the KEQ is greater than 1, the forward reaction is favored. And same thing, greater than, forward reaction. And now what we need to do is try this out. Okay, let's go ahead and try practicing solving a problem. And first thing we'll do is remind ourselves of the equilibrium equation. So we're going to have KEQ equals the concentration of the product and to the power of the coefficient multiplied by the concentration of the product times the power of the coefficient times, keep going for how many products you have, divided by the concentration of the reactant to the power of the coefficient times the concentration of the reactant times to the power of the coefficient times and so forth. All right, Next thing we should do is go through the story, the problem, and relate that back to the actual equation and see if we can figure out who would go where. So if we start with our reactant, we only have one in this case, and that would be N2O4. So the story tells us that N2O4, we have 0.0045 mole, but we have a liter of this, which means it's mole per liter. Okay, so now let's identify our product. Again, we only have one, which would be NO2. And our story tells us that we have 0.003 mole NO2. Let's also identify the equilibrium constant because that can come into play later. It's what is the equilibrium constant, which is going to be our x. All right, so now let's plug this information into our formula. So we're going to have x equals, let's now find our products because products go on the top, and our product is 0.030 mole per liter or molarity. Does it have a power or a superscript? The answer is yes, because we have a coefficient. Okay, so it'll be 0.030 molar squared. And we're going to divide that by our reactants. And our reactant we know is 0.0045 mole per liter or molarity. And there's no coefficient there, so there'll be no power. Let's talk for a minute about what that squared means. Whatever power is there, it means multiply the number inside the parentheses by itself that many times, right? So the way we could really write this, instead of 0.030 molar squared, we're going to end up with 0.303 molar times 0.303 molar, okay, divided by 0.0045 molar. Okay, and from there you stick it in your calculator. And that gave me 0.2. However, we need to go back and identify sig figs. And this guy has 2 sig figs, and this guy has 2 sig figs, so our answer needs to have 2 sig figs. So we need to put a 0 there. So the equilibrium constant is, for this particular reaction, is 0.20. Okay, not too bad. Okay, let's try one more. So this time we have KEQ equals concentration of the products to the x times, continue doing that, divided by concentration of the reactants to the x times, continue doing it. All right, so let's now identify our different pieces. We'll start with the reactants. So we have CO2. Does our story tell us anything about CO2? Yep, says we have 1.402 molar CO2. And our H2, our other reactant, says calculate the concentration of, which means it's going to be our X. Okay, if we look at the products, CH3OH, let's see, does it tell us anything about that? Yep, it says we have 0.818 molar of CH3OH. And the last is our equilibrium constant, which is 1.609. All right, let's plug this in. So if we start with our equilibrium constant, we have 1.609 equals the concentration of our products. In this case, there's only one product, which is 0.818 molar. And let's see, no coefficient there, so no power, divided by the concentration of our reactants. So we have 1.402 molar. No superscript, again, because there's no coefficient. And then calculate the concentration of H2, so that's going to be our X. But this guy has a coefficient, so he's going to be X squared. Oh, and that squared won't fit. Let's see if I can make this fit. X squared. So not working. Okay. 1.402 times X squared. All right. If I were you, what I would do is put 1.609 over 1, because that's basically the same thing, the same number, right? And so then you can cross multiply. So we end up with 1.609 times 1.402 times X squared equals 1 times 0.818 molar. Okay, let's stick some stuff in our calculator. Okay, and so on this side, on the left side, I got 2.25. Let's try that again. 2.256, and that's 4 sig figs because we have 4 here. X squared, sorry. And on the right side, we're going to have 0.818. Okay. Now, to get the X by itself, we're going to divide both sides by 0.256. And that gives us 0.363, because we had 3 sig figs here. So we're not quite done yet because we have X squared. We don't want to know the value of X squared. We want to know the value of X. So to figure out the value of X, we just take the square root of both sides, right? Square root, and that will give us X equals 0.602 with 3 sig figs. And there you go. That is how you calculate KEQ, or calculate the concentration of a reactant or product if you know KEQ. All right, that's it for today.